तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so let us resume where we left off. Remember that our general n dimensional autonomous dynamical system was specified by a set of first order equations. The vector x stands for a set of n variables and f is a vector field in this n dimensional phase space, and at each point the significance of f is that it tells you the velocity of the point in phase space, the dot of that x dot. X is the position of a point in phase space and x dot is its velocity, a change with time. So this vector field f specifies locally at each point in what direction the x is going to change, it is going to increase. So if in some part of phase space this point x, if this is the direction of f, it means in the next instant of time it moves along here, and at this point if this is the direction of f, in the next instant of time it moves along there, and so on, and you continuously join these little segments and you get the phase trajectory. So this vector field f has the significance of being the phase space velocity, velocity of the point in phase space, of the representative point in phase space. And our task is to solve this equation. I pointed out that in general this is not an easy task because f is a very complicated nonlinear function which combines all these variables and intricately mixes them up. But if you look at any typical point, local solvability is always possible, and the reason is, if I consider some arbitrary point x naught to start with, then in the immediate vicinity of x naught I can do a Taylor expansion of this function about the point x naught. And what would that look like? Well, if it were a single function, if you simply had f of x, then of course I would write this as f of x naught plus x minus x naught f prime at x naught plus etc. This is what I would normally do if I had a simple point, single variable x. If I have a set of variables x1, x2 etc., then again I do a Taylor expansion, but this is a joint expansion in all the variables. And for instance, if I had two variables f of x comma y, I would write this f of x naught comma y naught plus there is an x minus x naught multiplied by the partial derivative delta f over delta x at x naught y naught plus a term which is proportional to y minus y naught delta f over delta y at x naught y naught plus higher order terms. The higher order terms would typically have x minus x naught whole squared, y minus y naught the whole squared, and a cross term x minus x naught times y minus y naught, and then the partial derivative, the cross partial derivative, and so on. So all you need is to generalize that concept here to n variables, but in the leading approximation very close to x naught, it is clear you could throw away all terms except the leading term. And if you did that, then of course you realize that this equation becomes x dot equal to f at the point x naught plus terms proportional to x minus x naught itself. And therefore if you are sufficiently close to x naught, it suffices to keep this. If you are arbitrarily close, very close to x naught, then of course this is a constant. This matrix here, there is no dependence on any of the variables because it is at a particular point, the constant matrix, and you are back to the old situation where you have x dot equal to constant on this side, and that is trivial to solve because the solution is simply x equal to this constant times t plus at higher order terms and so on. So this is very trivial to solve, and what does it imply? It is a mathematical way of saying if I am here, then in the leading term all I have to do is to take this matrix, multiply, take this quantity here, this vector, multiply it by t, and that tells me what x is at t time delta t. So you are here at this point, and once you are here you repeat the procedure and you are here and then you are here and so on. So local solvability is not an issue, no matter how complicated this system is, locally you can always solve this. There is a rigorous mathematical way of saying it and it goes by the name of the rectification theorem. What it says is if you have such a function, then locally at every point you can find a change of variables such that the equation is trivial to solve, and that is exactly what we have done here. It is the mathematical theorem, I might as well write this down, it is called the rectification theorem. And in pictures it says the following: if this vector field f, if the phase trajectories look like this for the system, so an initial point here travels along this trajectory and a point here travels along that and so on, then in some neighborhood, some place here, some arbitrarily small neighborhood of my initial point x naught, the vector field points in this direction, and you go a little bit further away, it points in some other direction and so on. And what the rectification theorem says is in a sufficiently small neighborhood of any given point, normal point, you can find a change of variables from the set of variables x1, x2 up to xn to a new set of variables y1, y2 to yn. You can change variables where the y's are functions of the x's in such a way that this same neighborhood in y space looks like this. That is, all these vector fields have been rectified. In other words, in the y variables, this set of equations x1 dot is f1 of x1, x2 up to xn would start looking like y1 dot equal to 1, y2 dot equal to 0, etc. up to yn dot equal to 0. And the solution of this is simply that y2, y3 etc. remain constant and y1 alone increases linearly with t, and if this is the one direction, it says only the point 1, only the first coordinate increases, nothing else changes. Now this is rigorously establishable, and that is essentially what we have done here by saying to leading approximation this is a constant matrix. But of course you could ask what happens next. Well, the point is if you go to this neighborhood, then that same change of variables will not work anymore, you need a new change of variables. So from y you have to go to z or something like that, and that neighborhood here would look like this. Typically the vector field would start looking like this, and this is how the entire thing gets curved as you move along. And the difficulty with this program to implement it for all time is twofold. Typically what happens is these changes of variables would apply in certain neighborhoods, and it could so happen that as you keep going, you first start here in this neighborhood, then you go to this point, then you go to this, and then you go to this and so on. It is possible that this change of variables applies in a smaller and smaller neighborhood and therefore finally peters out to a point and the program does not work anymore. This is one possibility. The other possibility is that you go along and make these changes of variables in various neighborhoods. So both these things occur, both these phenomena actually occur quite often, and that is the reason why local solvability is not the same as global integrability. If I could solve this set of equations explicitly and write everything down as a function of time, then of course I can make t as large as I like, plug it in and I get a formula for the x. And that is global integrability. But this is local solvability. Locally I solve, but it cannot be extended to global integrability, and this is the problem. We will face this problem as we come along. There is really no in general, of course, systems are not integrable, and that is the way it is, and we have to look for alternative ways of handling this whole situation. But what is interesting is that in general this program would go through at every point, with one exception. When would this program not happen? When would this not work? When would it not be possible to say, okay, this guy here is just a constant vector c, this thing here is some c, and this would imply immediately that x of t equal to ct plus x of 0. When would this not work? If f is 0. If f of x naught is 0, then this program is not true anymore. So if the leading term in the Taylor expansion is 0, then you have to go to the next order term. And what is the meaning of saying that the leading term is 0? What is the meaning of saying that f at some point x naught equal to 0? What does this mean? It is a vector, and therefore it means every component is 0, and it means if you are at that point, the phase space point does not move at all, and therefore it is an equilibrium point or a critical point, more generally a critical point. So at a critical point, when this vanishes, when this vector field vanishes, then of course you have a singularity of this vector field. Incidentally, unlike scalar functions which you would say are singular when they become infinite or something like that, for a vector field you have a singularity even if the field vanishes at some point, because then you do not know in which direction it points completely. So even the ordinary vector, the vector r, the position vector r, at the origin is singular because it is not defined at that point. At the origin this field is not defined, its direction is not defined, and if you drew the field lines of this vector, of course you realize immediately why, because the field lines look like this. At any point things look like this in this radial fashion, and of course at the origin it is indeterminate. So vector fields become singular even when they vanish, and that is exactly what happens at a critical point. What would you do then? And let me therefore define this now. Let me write this. And I will abbreviate it with CP. Now once you are at a critical point, and in our mechanical examples critical points would correspond to equilibrium points, in a more general context it just be singularities of some kind with various interpretations. Once you are at a critical point, then this program of rectification does not work anymore, and you have to go to the next term. And what would that be? So let us suppose x naught is a critical point, I am at a critical point, and without loss of generality let me take the origin to be at a critical point, because I could always shift the origin in x without too much trouble in these problems. So let me assume that I focus on one particular critical point, and let me call it for the moment the origin. So f of 0 is 0. What should I then write? When I do a Taylor expansion, what should I write? Yeah? What should I write? How do I do a Taylor expansion in variables? Yes, I have x minus x naught delta f over delta x plus y minus y naught delta f by delta y plus etc etc. This is the first order term. So how should I write this in general? What should I write it in general as? Well, no, I would like to have a compact formula for the n dimensional case, right. What should I should dot something with something, so what should I dot, what should I dot what? X dot gradient. But f is a vector, f is a vector, right. So what should I do? Yeah, you're right. So what should I do? Are you more comfortable with index notation? With index notation, I mean whichever way you like. We have x1, x2, x3, so let me call it x sub I, and then of course you have xi dot equal to xi multiplied by delta which f? Okay. This you got to be a little careful about. I mean there are too many repeated indices. The index notation says that if you have an index I on the left hand side, it should appear on the right hand side as well. If you have an index j on the left, j should appear on the right as well. Every free index which appears on the left must appear every time on the right as well, and every repeated index is summed over. So the notation is very simple and self correcting. Free indices will appear only once on either side of the equation. A repeated index will appear twice, and it is a dummy index, it is summed over. If it appears thrice, you made a mistake. It's as simple as that. So this does not look very good to me, so what should I do? Well, look at the following. You have x1 dot is approximately equal to x, we put everything at the origin, so it is equal to x1 delta f1 over delta x1 plus x2 delta f1 over delta x2 plus etc., isn't it? The equation for x1 dot involves only f1 on the right hand side, and I am Taylor expanding that function about the origin, and therefore you have first order terms in x1, x2, x3 etc. So this gives you a hint. What should I write here? Write this as xj, this is fine. So we have a free index f on the left, I on the left and 1 on the right, so it is fine, each has a vector, and then the index j is summed over. In vector notation, how would I write this? X dot approximately equal to what? Xj dot del, xj, well, x dot, yeah, x dot del, yes, operating on f. You agree with this? Yes? This is a scalar operator, acts on a vector, produces a vector, and this is a vector on the left hand side. So is this fine? Good. So you write it in whatever notation you like, write the equations out if you like, but it is fine either way, plus higher order terms which require more indices to write down and so on. But now let us make an assumption that the critical point we are involved with is a simple critical point. By that I mean that this matrix, this set of numbers evaluated at the origin, by the way all these things have to be evaluated at x equal to 0 because you want everything at the critical point. So this matrix, this is a matrix because it has got two indices now, that Jacobian matrix you should assume is not singular, because if that is singular then you have a higher order critical point and things become more complicated. So the initial assumption is that this Jacobian matrix is not very singular. What then do the actual equations look like at this point? Let us write it for the 2 by 2 case, the 2-dimensional case, and then you see the generalization to the n-dimensional case is obvious. So in the 2-dimensional case, let me just write x dot equal to f of x y and y dot equal to g of x comma y, just so that we have two different functions. Instead of f1 and f2 I will call them f and g, and instead of x1 and x2 I just call it x and y, and you look at what happens. Then this is n equal to 2. Critical point given by f of x comma y equal to 0, g of x comma y equal to 0. That is where the vector field vanishes. Okay. Now typically f of x comma y equal to 0 is a curve in the xy plane, and so is g equal to 0, and generically two curves in the plane would intersect at isolated points, and those points are your critical points. Then take any one of those critical points, let us call it the origin, this critical point the origin, and we would like to see what the system does near the origin. And the statement is, I write near the origin x dot equal to f of 0 comma 0, but that is 0 by definition because it is a critical point, plus x times delta f over delta x at the origin, let me just denote it by 0, plus y times delta f over delta y at 0, plus higher order terms proportional to x squared, xy and y squared, and then cubic terms and so on. And similarly y dot is f of 0 0, that is 0 by definition, plus x delta g over delta x at the origin, plus y delta g over delta y at the origin, plus higher order terms, plus higher order terms. So what have you succeeded in making your system look like? It is evident now immediately that in the close vicinity of the origin this system looks like x y d over dt equal to a b c d x y, where a b c d are these 4 partial derivatives evaluated at the origin, and they are numbers, and the assumption is this is not a singular matrix. What has happened then? What sort of system has this become? A linear system. It has become a linear system. So in the vicinity, immediate vicinity of a simple critical point, the system has been linearized, and now we know how to solve linear equations because we know that the solution is the exponential in time. And this is our trick, this is going to be our basic trick. So this linear matrix L, this is nothing but the Jacobian Fg over delta x y evaluated at the origin. This is a shorthand notation for this set of partial derivatives all evaluated at that point, and you put them in a matrix, and then the equation looks like d over dt of the position of the representative point in phase space, its position in phase space is a matrix, a constant matrix multiplied by the vector itself. So the system has been linearized. Yeah.
If it is not singular,
yeah. Yes, it will become intrinsically non-linear, exactly. If it is singular, well, we will come to this. If these partial derivatives vanish, for example, two cases, one is all the partial derivatives vanish, in which case it becomes a nonlinear system. The other possibility is it does not vanish, but the determinant of this matrix is 0, and then of course you have a situation which is singular, and we will see what happens when it is singular. You will see that it becomes degenerate in a certain case, in a certain sense. We will look at that case in some detail. Okay. But generically, typically you do not expect bad behavior, you expect these functions f and g would have first derivatives at typically at every point, and therefore if the slope is defined, slopes are defined at that point, you have a matrix L, and you have to deal with this linear problem. which is of course well known to us. And what does that solution look like? Well, we know that x then equal to e to the LT times x at 0. This is x at time t. Sufficiently close to this point, therefore, in the immediate vicinity of this critical point, a trajectory would behave, its time dependence would be given by this exponential here. Not at the critical point. At the critical point, if you start with an initial condition at the critical point, you remain there because that is an equilibrium point. But in its neighbourhood, if this therefore is your critical point, in its neighbourhood wherever you start, whether you move out or you move in will depend on e to the power LT. And on what property of L would this depend? On the eigenvalues. If the eigenvalues have positive real parts, you would have a behavior which grows with time. If they have negative real parts, things would fall into this, and if they have 0 real parts, you expect that, what would you expect? Pure, you would expect oscillatory behavior, you would expect things would go wrong. This was the lesson we learned from the harmonic oscillator, and this is exactly what we are going to codify. So everything is going to depend on the set of eigenvalues of this matrix here. Now there are two ways of doing this. One of them is to just write down the general case, and the other thing is to do the 2-dimensional case in a little more detail. So I would prefer to do the 2D case in more detail because you can see geometrically what is going to happen. So for some time from now on, let us continue and focus on the 2-dimensional case, and I will just continue with this notation. Instead of x1 to x1 and x2, I just use x and y, and let us continue with this notation. Now what happens next? Everything would depend on e to the power LT, and I told you that the simple ways of finding out what e to the power LT is. By the way, you do not need to, again I emphasize, you do not need to be able to diagonalize L. All you need are its eigenvalues, and they are fairly easy to find. And do you know how to exponentiate this matrix? How to explicitly find e to the power LT? For an arbitrary 2 by 2 matrix, this happens to be possible. Not so for an arbitrary 3 by 3 or 4 by 4 or n by n matrix, but in the case of a 2-dimensional matrix, just 2-dimensional matrix, arbitrary 2 by 2 matrices, this turns out to be fairly easy and simple to do. And let me spend a few minutes, digress and do this. So we will look at some examples and then you get some practice doing this. You see, the difficulty is that if you took a matrix L equal to A, B, C, D, and you want to find L squared, L cubed and so on, this can be extremely tedious, and the reason it becomes tedious is because this is shorthand for A times 1 0 0 1 plus B times 0 1 0 0 plus C times 0 0 1 0 plus D times 0 0. This thing here is shorthand for that, and these are the 4 basis matrices, the natural basis for 2 by 2 matrices. In the language of linear algebra, that is the natural basis, and this is what you mean by a matrix. Okay. However, the problem arises, sorry, this should be a 0 here. The problem arises because these matrices, their commutation properties are not trivial. So if you take 2 of these matrices and ask what is the product and what is the product in the reverse order, they are not necessarily equal to each other, and you can see that this gets fairly complicated as you go along. So what one would like to do is to change the basis to a better basis where the mutual commutation properties between the basis vectors, basis matrices, is a little simpler, and these are the famous Pauli matrices. So you have of course the unit matrix which is 1 0 0 1, you have the first matrix sigma 1 equal to 0 1 1 0, sigma 2 equal to 0 minus I 0, sigma 3 equal to 1 0 0 minus 1. These are called the Pauli matrices. Are you familiar with these matrices? Yes, some of you are, some of you aren't. Never mind, it is actually quite simple. These matrices have very interesting properties, they call the Pauli matrices. And they are linearly independent of each other, and it is an elementary statement to say that any arbitrary 2 by 2 matrix can be expanded uniquely as a linear combination not of just these 4 basis matrices but of these 4 basis matrices. So you could write any arbitrary 2 by 2 matrix as a linear combination of I, sigma 1, sigma 2 and sigma 3. Okay. That is a simple exercise, I leave it to you to do that, because start with this A, B, C, D and insist on writing it in this form. So write this thing as this same matrix, write it as alpha naught I plus alpha 1 sigma 1 plus alpha 2 sigma 2 plus alpha 3 sigma 3, and you see immediately that alpha naught, alpha 1, alpha 2, alpha 3 are linear combinations of A, B, C, D, and you can solve for one set in terms of the other and vice versa uniquely. So this immediately shows that you could expand a matrix in this basis as well. There is no restriction that the alphas have to be real or anything like that, because as you see one of the basis matrices itself has got I out there. The advantage of this basis is that these matrices are Hermitian, they are equal to their complex conjugate transposes. That is not true here. On the other hand, these matrices have that symmetry property, and it is also a simple exercise to show, and I am going to give this as a problem set to work out all the properties of these guys. Sigma I squared equal to the unit matrix. The square of every one of these matrices is equal to the identity matrix. Moreover, sigma I sigma j plus sigma j sigma I equal to 0 if I not equal to j. They anti-commute with each other, and that is a very, very powerful property for what we want to do, because if you want to write e to the power Lt, you write e to the Lt equal to e to the alpha naught I plus, let me call it alpha I sigma I with a summation over this index I implied. Looks almost like a vector, alpha dot sigma, except you must remember that the components alpha 1, 2, 3 need not be real numbers, could be complex numbers in general, and we have the task of finding this quantity here. Now what is this equal to? Well, you know e to the power a plus b is not equal to e to the a times e to the b in general, where a and b are matrices, and the reason is e to the power a would have only powers of a and e to the b would have only powers of b. So if I write e to the power a multiplied by e to the power b, all the a's are on the left and all the b's are on the right, but that is not true when I have a plus b in the numerator. So you can see that e to the a, e to the b is I plus a plus etc, I plus b plus etc, and if I work this out and write it out, all the a's stay on the left and all the b's stay on the right, but if I took e to the a plus b equal to I plus a plus b plus 1 over 2 factorial, and what is the next term? What is the quadratic term? It is a squared plus ab plus ba plus b squared. So you see there are terms which have b on the left and a on the right, and as you go to higher powers more and more of this will happen. There will be combinations like b, a, b, a, b, a and so on, and that is not allowed for here. So this is not equal to, this quantity is not equal to that for matrices or for operators in general. On the other hand, if I look at this quantity here, and this is alpha 1 sigma 1 plus alpha 2 sigma 2 plus alpha 3 sigma 3, and I expand it out, this quantity commutes with everything, so you can actually move it out. You can write this as e to the alpha naught I multiplied by this thing here, but when you expand the exponential here, You get terms like sigma 1 squared, which is the identity, sigma 2 squared the identity, sigma 3 squared is the identity. Then you get combinations like alpha 1 alpha 2 sigma 1 sigma 2 plus sigma 2 sigma 1, but that is 0 because of this anti-commutation property, and therefore you can actually find the exponential. When you take any two of these in opposite orders, it anti-commutes, they vanishes, completely vanishes. So I leave the rest of this as an exercise to you to actually work out what e to the power alpha naught I plus these guys is. You can write a very compact formula for it in terms of the alphas completely. What would you expect? What would you expect is the final answer? After you go through this entire rigmarole, what would you expect? Nothing very complicated, because this is also a 2 by 2 matrix, and we just said that every 2 by 2 matrix could be uniquely expanded in terms of the identity matrix and the Pauli matrices. So the final answer has to be something of the form some beta naught I plus beta 1 sigma 1 it has to be of that form, and there is no option, nothing but that. All that happens is the betas are complicated functions of the alphas, in this case not very complicated. So I leave you to work this out, and that will tell you how to exponentiate such a matrix. This is a very simple formula which once you remember the formula or work it out, you can apply in every given case, and this is the answer here. Okay. Our interest, however, is not in finding the explicit solution, but in finding the nature of this solution. We would like to find out what does this do, what kind of behavior do you have in the neighborhood of the critical point at the origin. This is our target. So let us start classifying it, let us start finding out what we should have and what the possibilities are. So let me call this classification. So I classify all the possible critical points in 2 dimensions in the xy plane. The first possibility is that lambda 1 lambda 2 are greater than 0, 2 real eigenvalues both positive. Now let us list all the possibilities and then look at pictures to see what happens. The second possibility is lambda 1 lambda 2 less than 0. Incidentally, the situation where the eigenvalues become equal to each other and both positive or both negative is a special case, that is something we can handle quite easily. The third possibility is one of them positive and the other negative. This is possible too. And the fourth, remember we have assumed that the matrix is not singular, so we do not allow for a 0 eigenvalue at the moment. What is the next possibility? They become complex, these things become complex. So certainly you would have lambda 1 comma 2 equal to lambda plus or minus I mu, where lambda and mu are real numbers, and lambda is greater than 0, the real part is positive. That would mean an exploding exponential. The next one is lambda 1 comma 2 equal to lambda plus or minus I mu, and lambda is negative. And there is one more possibility, lambda equal to 0, pure imaginary but not 0, pure imaginary eigenvalues. So the last of these is lambda 1 comma 2 plus or minus I mu. That is it. This exhausts everything, and all we have to do is to look at each of these cases and find out what kind of critical point it is, and you have various types of critical points, and you have then succeeded in classifying all those critical points for 2-dimensional flows where you do not have a higher order critical point or you do not have a degenerate map. Let us see what happens. A simple way to do this is simply to look at an example, draw the picture and then argue that the general case is a distortion of this picture. So let us do that. Let us look at case 1, which is 2 eigenvalues positive, and I look at an example always. So let us look at x dot equal to, it has got to be a linear function of x, and that function has to vanish when x is 0 and y is 0, because we are looking at the neighbourhood of a critical point which we have assumed is at the origin. So let us look at this. That certainly satisfies the criterion, because in this case lambda 1 is equal to lambda 2 is equal to 1, both are positive. Since we do not want that kind of equal degeneracy, so let us make this 2y. What do the flow lines look like, and let us try to draw the picture directly. So here is the x axis, the y axis, and I would like, and this is the origin, that is the critical point, and we remember I have magnified this figure so that I am very close to the critical point, but I have just blown up this figure to see what the trajectories look like and what would they look like. Well, a good idea is always to start with special trajectories and then look at the more general case. So suppose I start with an initial condition here, very close, y is 0, and therefore it never takes off, this guy does not take off, and x dot is x, and it says x is increasing because x is positive, and in which direction is this flow going to be? It is going to be outwards, that is a trajectory by itself. So wherever you are on this point, on this line, you are just going to move outwards along that. So you really do not care, it is a whole family of initial conditions you have taken care of. Had you started on this side, then of course you would move in the negative direction. Remember, we are not interested in how you are moving as a function of time. This says x goes like e to the t times x naught. So whatever be x naught, it is just multiplied by e to the power t, it moves off. If you start with y, then of course you go there and you go there. You start now away from the axes. So we have taken care of the 4 axes, you start with an initial condition, let us say here. What would it do? Well, it would tend to increase x and it would tend to increase y, but remember x goes like e to the power t times x of 0 and y goes like e to the power 2t times y of 0, and you could in fact eliminate t between these two and you discover y is proportional to x squared. So from here what would you do? You move in a parabolic path, so you really get off like this, in this fashion, and if you started here you move off like this, if you started here you do this, and if you started here you do this, okay. Except if you start on the axes, you are always going to be on one of these curves. Remember, the actual flow, once you move sufficiently far away from the critical point, you would have to include nonlinear terms, higher terms, and then it would change, but in the infinitesimal vicinity of the critical point, this is what the flow looks like, and wherever you are it would do the same. Except for this point. So the entire neighbourhood has this set of trajectories moving out, and these two like this. So it is as if wherever you are you have a common tangent, the x axis, and there is one exceptional direction, the y axis. Why? Yes, but I could start with x naught here, and that would also lie on its own trajectory. So whatever initial condition I start on, I am part of a parabola. So I have a family of parabolas, some pointing up, some pointing down in this fashion. So this is what the picture looks like. Now would you call this a stable point or an unstable point? Unstable, because in every direction it is being thrown out, and therefore we should really properly put a cross here and immediately call this an unstable. It is called an unstable node. There are different terms for this, but I will use one set of terms once and for all. It is an unstable node. Case 2 is trivial to solve. Incidentally, the case when the two eigenvalues are equal, what would happen then? It would still be an unstable node, but what would happen if you did not have this 2 is that both of them would go like e to the t, and the ratio would therefore be a constant, which would mean that the ratio, that these are straight lines. So the picture would really look like this. You would get a kind of star pattern. This would is what would happen if lambda 1 equal to lambda 2 greater than 0. That too is an unstable node. Okay. The difference between these two pictures is that here there is a common tangent with one exceptional trajectory direction, but here there is no such thing. Every direction is allowed in this fashion. So this radially outward pattern immediately tells you that it is an unstable node. So does this. What would happen if both these things were negative? Case 2, all I have to do is put minus signs. What would happen to this picture? All the arrows would be reversed, everything would flow in asymptotically. Would you call this stable or unstable? I would call it asymptotically stable, because I am going to distinguish between stability and asymptotic stability, and they are different properties altogether. So things would flow in and be asymptotically stable, so all arrows reversed, everything reversed, etc. We will not bother to do the rest of it, and this is an asymptotically stable node, asymptotically stable node in this case. Let us look at case 3, which is interesting. So case 3, the simplest way to do this is to put x dot is x and y dot is minus y, or let us put it as minus 2y. The two eigenvalues are 1 and minus 2 in this case, and things are flowing in the y direction but exploding in the x direction, and what would the picture look like? Once again, if I start at y equal to 0, then x just increases with time, so this is certainly a trajectory, and so is this a trajectory. The moment you have things going out, it means it is unstable, so let us just put a cross there right away. The moment you have things flowing out in some direction or the other, it means the system is really unstable, and you put a cross, and in y things come in. So if I start with x exactly equal to 0 to start with in the initial condition, then of course things flow in. But if I do not do that and I start here, what would happen? Yes, exactly. So the whole plane is striated by these curves which look like hyperbolas, but of course they are not hyperbolas, and the reason they are not hyperbolas is because x increases like e to the t, but y increases like decreases like e to the minus 2t. So you do not have xy equal to constant, x squared y equal to constant, it does not matter. So it has still got a shape which looks roughly like this. They are not hyperbolas, but it is called a hyperbolic point or a saddle point. So this is a saddle point, unstable, saddle point. Next, case 4, and lambda is positive in this case, what would it look like? This is a little trickier, a little harder to do. We could write down examples which would do this, but we can argue this out even without writing down a very simple example. But mind you, you have to object at this stage and say, well, how do we know this is true even if you had more complicated flows? I assumed extremely simple flows. I said x dot is x, y dot is y or minus y. So I decoupled x and y, and the question to be asked is, if you couple x and y, if you have general linear terms which involve both x and y, how do we know this is still true? I have to still convince you that this is exactly what is going to happen. We will come to that in a minute, but let us finish the classification. and then we go back and I tell you what happens in the general case. Now what would happen there is that both x and y would have terms like e to the power lambda t, e to the power I mu t, plus or minus. Both x and y would have linear combinations of this. This quantity here is simply cosines and sines, they just oscillate. But e to the lambda t, when lambda is positive, it explodes outwards. So you really have oscillatory behavior such that the sign of x and y would change between positive and negative, but the magnitude would increase in this case. So it would be an unstable spiral. So in this case it is clear that the picture is going to look like, it is going to go outwards. Which direction it moves in, etc., is a matter of detail, but it is something which gets out, and therefore it is not too hard to see that this is an unstable spiral point. There are other names given to this. One of them is focus, and sometimes it is called vortex or whatever, but we just call it an unstable spiral point. Yeah.
If mu tends to 0,
yeah,
then it should be the first one, right? How
yes,
does it become
yes, that is a good point. If mu goes to 0, this fellow should tend to the case of the unstable node. Now we will see explicitly how this happens. We will see distortions would occur in here, and we will see what happens. Okay. You can see that immediately in some sense. If mu goes to 0, the time period of this oscillation, the frequency of the oscillation is mu, so the time period of the oscillation is infinite. So you can see that it never completes a spiral, it will just move out or move in immediately, but we will see this explicitly. Okay. What would I call this? It would just be an asymptotically stable spiral point, things would flow in. This is what happened in the case of the damped simple harmonic oscillator. So this is an asymptotically stable spiral point. And finally the case of pure imaginary eigenvalues. We have already studied one case, the simple harmonic oscillator, the undamped oscillator, and what was that critical point? There were ellipses, they were like ellipses, but it was a center. This point is called a center. So let us write the oscillator case once again down. We say x dot equal to v dot equal to minus omega squared x. So in this case L, the matrix was 0 1 minus omega squared 0, and lambda 1 comma 2 was equal to what? What are the two eigenvalues of this matrix? Plus or minus I omega. It's obvious that it is a plus or minus I omega. That is why the solutions look like cos omega t and sin omega t. We know that, right? And they neither went in nor went out because there was no exponential factor pre-multiplying the cosine or sine, and this was a center. Would you call it stable or unstable? It is certainly not unstable, but it is not asymptotically stable either. It does not fall into this point. I would call it stable, and that will tell us how to distinguish between stability and asymptotic stability. Notice this is the only place where I have used the word stable. Everywhere else it is either mean unstable or asymptotically stable. At that point is just a stable point. And what was peculiar about this problem which is not there everywhere else? Periodic. This corresponded to periodic motion. The moment you have a center, you have periodic motion. None of these motions is periodic. They are either damped periodic motions or they are motions without any such periodicity, but this is the only one which is periodic. And it is delicately balanced. It is periodic because the linearized matrix around the critical point has exactly 0 real part, and you see how accidental this is. So we will see that periodic motion is quite exceptional, things have to be just right. The little bit of friction here and it is gone completely, a little bit of positive feedback and it explodes the other direction. So maintaining periodicity is not so easy, and they are really very delicately poised, and we will see it is going to give us a lot of headaches periodic in the general case. Okay. Now let us come back and answer this question of why did not I look at the general case, why did I do this, and my answer is the following. My answer is that the eigenvalues, they determine whether the thing is stable or unstable or asymptotically stable, and these eigenvalues are independent of linear transformations that I make on these matrices. If I took a matrix and did a similarity transformation on it, then the eigenvalues do not change, and that is easy to see because what are the eigenvalues of L? L is A, B, C, D, and the secular equation is lambda minus A, lambda minus D, minus B minus C, 0 equal to this, equal to lambda squared minus lambda times A plus D plus AD minus BC equal to 0, and the eigenvalues therefore lambda 1 comma 2 equal to A plus D plus or minus the square root of A plus D the whole squared minus 4 times AD minus BC over 2. But do these combinations remind you of anything? What is A plus D? It is the trace of the matrix, it is the sum of the diagonal elements, it is called the trace of the matrix. So I have trace L equal to T equal to A plus D, and what is AD minus BC? It is the determinant L equal to D. The eigenvalues can therefore be written as equal to T plus or minus square root of T squared minus 4D over 2. And this tells you that the eigenvalues of a 2 by 2 matrix do not really depend on all the elements in some independent fashion, but only on 2 combinations, the trace and the determinant, and both these are independent, are invariant when you make a similarity transformation. Okay. So what we will do is to start at this point and exploit this invariance to argue that we do not have to study the case in generality in each case explicitly. What we have here based on our simple example suffices. This already tells us this is the general case as it stands, and I will exploit this invariance here to talk about this. By the way, this should be true for 3 by 3, 4 by 4, so I leave it as a homework exercise for you, next time we will talk about it. What happens in the 3-dimensional case? What would the eigenvalues depend on? They should also depend on combinations which do not change when you make similarity transformation on the matrices. You have trace as one of them, determinant is one of them, but you need a third because there are 3 eigenvalues in that case, and in the n-dimensional case you need n of them. So think about this and we will come back because it has some significance. Let me stop here.